So this is the start of Unit 3, where we'll be talking about transformations of functions. But before we even get there, we have to look at what we call parent functions. So if we want to sort of look back into what we've done in senior school math for up to this time, in grade 9 we studied linear functions, but you can think of it as the parent function, or the most basic form of that function. That's what parent function really means, is y is equal to x. Yes, we've learned the form y equals mx plus b, where a line has a slope and a y-intercept, but really we think of the most fundamental form of that line. A straight line is just y is equal to x. Then when in grade 10 we studied quadratics, in other words, when the x is squared, y is equal to x squared was the parent function, and we actually started exploring parabolas of the form y equals x squared. And then we discovered that, well, any equation, in other words, any quadratic equation where the x is squared, so it would be x squared plus 6x plus 9, whatever it is, it's all going to have that general parabola shape. But the parent function, or the most basic form of that function, is y is equal to x squared. Well, in grade 11, we're going to explore 3 other parent functions to add to your sort of repertoire, or just sort of get a feel of what these functions look like. So our first one we're going to look at is a cubic function. So we're not going to do decimals, but we're going to explore this with a table of values. So when we talk about cubic function, we're talking about the x. So the exponent on the x is actually 3. So it's going to be x cubed. So this is the most basic form of a cubic, and we're going to see what this kind of looks like. So when we go off a table of values, we could really pick any values of x and start plotting the values of x and whatever y we get for that x. But we want to take a really strategic approach to this. So for me, I always like to start with x being 0. In other words, when x is 0, what's my y value? With 0, we discover has wonderful properties and attributes. It's actually a great number in math, my favorite math number. And it makes sense that that's going to be a starting point. So when we say here f of 0, that's really going to be 0 cubed, and well, that's because the answer is going to be 0. Then our next step might be, well, let's start incrementing x by 1. So what does x being 1 look like? So that's going to be 1 cubed. So that's just going to be 1, 2. When x is 2, we get 2 cubed, so it's going to be 2 times 2 times 2, which is 8. And finally, the last value we're looking at for x, in the positive direction, it might be 3. So we get 3 cubed is equal to 27. And hopefully that gives us enough information to sort of give us a feel of what this graph looks like. Now we also will look at x in the negative direction. So in this case, what happens if x is negative 1? So here f of minus 1 is going to be negative 1 cubed. Well, negative 1 times negative 1 times negative 1 is just going to be negative 1. And then when x is negative 2, so that's going to be negative 2 cubed. It's going to be negative 8. And negative 3, it's going to be negative 3 cubed, which is minus 27. So we can see that this is different than a quadratic, because we do get some negative answers. In this case, when x is actually negative, we do still get a negative answer. Unlike a quadratic, we'll always get a positive answer. But like a quadratic, we do see a little bit of symmetry here, although it just was a positive number and then it was a negative number. So for example, when x is 2, we get a positive 8. When x is negative 2, we get a negative 8. So this is the idea of a little bit of symmetry here, and maybe when we look at the graph, we could see it as well. So let's go ahead and plot these points. So we got 0, 0. So our grid is nicely labeled, scaled for us, because it's going to recognize that we have some pretty big y answers. So answers for y. So we got 0, 0, and then we got 1, 1. So it's going to be a little bit tricky. So maybe that might be right over there like that. And then 2, 8. So not quite at 10. And then finally, when we hit 3, that explodes up to 27. So then we got some points over there. Likewise, we're going to go in the x equals negative 1, or when x is negative. So negative 1 and negative 1 might be right there, maybe. And negative 2 and negative 8. and finally negative 3 explodes down to negative 27 or something like that. So the magic question is, how do we connect dots? Do we do it through straight lines? Is it some sort of, is it just a smooth curve? What's happening in between those dots? So this is where a program like Desmos, GeoGebra, will really help us out, and that's really what it's doing for us, is taking all the different values of x that we can think of, plug it in, and plotting it for us. We can do the same thing with the calculator. Plug in 1.1, 1.2, 1.3, get those intermediate values of x and see what the pattern is going to look like to eventually get the shape of our curve. Well, I'm going to shortcut it and just tell you that the shape is going to be like this. So it gets really flat as we get to the origin because the point's really low, and then it's going to explode up like that. So that's what a cubic function looks like. And to me, how I could describe it is maybe like a yin-yang. So there is a little bit of symmetry here. The line of symmetry is actually the y is equal to minus x line, where basically you flip that, you get the it's reflected over that line. Another thing you can kind of see is that if you spin this around the origin, you spin it like 180 degrees, it's going to fall upon itself as well. So that's another neat thing about the graph of this function. So let's look at the characteristics. The domain here is, well, it's going to be any real number, and that's it. In other words, we could put any number in there and we could cube it. We're always going to cube it, and we're always going to get an answer. And really, for the range, we're going to see that we could get any answer as well. So special features, so this is a curved line, and maybe you could think of it, it looks like a yin-yang. It's symmetrical. Across y is equal to minus x. Okay, and so in this case, we're going to say that also goes forever up to the right and down to the left. So very similar to the method, let's say y is equal to x, a straight line, except this time it's actually a curved line that has a similar feature. Okay, the next function we're going to look at is the square root function, or the root function. So f of x is equal to root x. Now, one thing to note is when we did units 1 and 2, I highly emphasize that whenever we take a square root of a number, so in other words, when we say square root of 9, we don't come up with one answer. There's actually going to be two answers. It's going to be a positive answer and a negative answer. So in other words, plus or minus 3 would be the answer. But we can't look at that as a function because that is itself is not a function. We can't, there's not a definitive answer. So when we say f of 9, if it's positive and negative 3, that's not a function. So what we're really looking at here is just the positive values. So that's implied. If we want to look at both values, we'll actually write the plus and minus in there. But because it's not written, it's implied that we're only looking at the positive answers. So how will we go off again and graph this? Again, same thing, I'm going to start at 0. So maybe we're going to write 0 up here. And so f of 0 is going to be root 0, which is just 0. So again, increment x by 1. So look at f of 1. So square root of 1 is going to be 1. Now we could increment x again to go to look at 2. But this one would be difficult to graph because when we take the square root of 2, it's not an exact answer. Some decimal answer, 1.22 something. It's going to be hard to graph. So what we want to do in this case is keep going till we get something to get an exact answer for the square root of x. So 2, square root of 3 is not exact, but square root of 4 does work out. So here we look at 4. Square root of 4 is going to be 2. And again, we keep going up, 5, 6, 7, 8, 9. So we're looking at the perfect squares. The square root of 9 is going to be 3. And maybe one last one we're going to look at is 16. So square root of 16 is going to be root 16 is going to be 4. And maybe we'll look at one more because I can't see in the graph here. We do want to kind of go up a little bit. So in this case, we're going to go root 25. That's going to be 5. So let's look at x in the negative direction, so negative 1. So f of negative 1, which is going to be square root of negative 1. And here we discover, oh, we can't get an answer. And there is no number multiplied by itself will give me the answer of negative 1. In other words, if a number is either positive, so positive times positive is a positive, or a number is either negative, so negative times a negative is going to be positive. So we can never do a square root of a negative number. So in this case, we get no answer. So this is the second thing we discover in math. It's the second thing we do in math, and we can't get an answer. The first one was divided by 0, and we call that answer undefined. In this case, the square root of negative 1, there's no answer to that. We can't do it. So obviously we can't do that for negative 2 as well. We get no answer. So let's plot these points and let's see what we get. So we get 0, 0. So a bit of an interesting scale we have here. So we're going to plot this carefully. 1, 1 might be right there. 4, 2 may be right around there. 9, 3. So we have a little bit more than halfway there. 16, 4. And then 25, 5, 25 might be out here. And we get 25, 5 over there. So again, we're gonna, if we plot in various values of x and plot it, if we did it in Desmos or GeoGebra, we're gonna get a graph that looks something like this. So it's still curved, but what we're gonna recognize is it gets flatter and flatter as x gets bigger. So let's look at the domain of this. So here we're going to see that the domain is something that's different than we've ever seen before. In case that x is a real number, but in this case, x can only be certain values. In this case, x can only be greater than or equal to 0. In other words, we can only square root a number that's either 0 or that's positive. The range and what are our possible answers. So here, y is going to be ER. Element of the real number system as well. And since we're only looking at the positive by definition, therefore the answers that we get must be greater than or equal to 0 as well. So some of the special features here I have, so this is a curved line as well. As x gets bigger, the line or the curve gets more flat. But it will never be completely flat because when we do a square of a number, we'll never get the same answer. So for every value of x, we're always going to get a different answer. But just as x gets bigger, the difference between the answers is going to be smaller and smaller and smaller. So that's another thing we kind of make note of is the function is always increasing. Even though it's not increasing by a lot, as x gets bigger, it is still increasing by even the smallest amount. So in other words, this curve will never point back downwards, and never heads back down towards 0. So it will always keep going up and up and up. So that's what the square root of x looks like. So our next function we're going to look at is the absolute function. So the absolute function represented as a notation, it looks like that. So we got two vertical bars around what we're taking the absolute value of. So here is the absolute value of x. So what does the absolute value mean? It means that we take a value and we ignore the sign. So in many instances, this is kind of termed as the magnitude. So when we look at maybe physics or something like that, we talk about just a magnitude and not a direction. So sometimes a negative value might imply a direction. So for example, when we take 3 steps to the right, we may say that's positive 3, but if we take 3 steps to the left, we may say that's negative 3, but how many steps do we actually still take? In both instances, we take 3 steps. If we look at the number line, when we have positive values, we go to the right. But we have negative values, we go to the left of the 0 on the number line. So we still go a certain amount, it's just that we're going in a different direction. So that's what absolute value or the magnitude really kind of means. So if we look at, again, we're going to look at a graph, and we might start at x being 0. So here was f of 0. That means we want the absolute value of 0, which is just 0. 0 has no sign, but it's just going to be 0. 1. So what's the absolute value of 1? Well, that's just going to be 1. What's the absolute value of 2? Well, it's just going to be 2. And maybe the last one we'll look at is absolute value of 3. Well, that's going to be 3. Not very exciting. So let's look at x in the negative direction and see what properties are what's showing up there. So what's the absolute value of negative 1? Well, we take the sign away, so it just becomes a positive 1. Well, negative 2, the absolute value of negative 2 is just going to be 2. And the absolute value of negative 3 is just going to be 3. So like the parabola, there is a bit of symmetry here where we have a positive, we have the answers kind of repeated based on a symmetrical look at the x value. So in terms of graphing this, I'm actually going to change the scale on this. Let's go up by ones, just like we did with the x scale. We'll do that with the y scale as well to get a little bit more accurate picture of what this looks like. So we got 0, 0, 1, 1, 2, 2, 3, 3, and likewise we have negative 1 and 1. So negative 1 and 1, yes, negative 2 and 2, and negative 3 and 3. So how do we connect these dots? Well, hopefully we kind of see that it should be a straight line. Since, for example, what's the absolute value of 0.5? It's just going to be 0.5. What's the absolute value of negative 0.5? It's going to be negative positive 0.5. So there's a definite linear relationship or direct relationship there between the x and the y values. So we will connect these with an absolutely straight line. So our graph does look like a V. So we want to think of this as, I don't know if this is the correct term or not, but we want to look at it as the vertex, or really the bottom of a graph. It is going to be pointed. So unlike a parabola where it's a nice smooth curve, it's actually pretty flat at where the vertex is going to be. In this case, it's going to be on the absolute value, it's going to be pointed. So we can discover the domain and range is exactly the same as we have for a quadratic. So the domain is really all real numbers. In other words, we take any number, 3.6594, you take the absolute value of that. The range, well, it's going to be any real number, but in this case, we're only going to get 0 or a positive answer. So in other words, y is always going to be greater than or equal to 0. So the special features here, so it's not a curve, is really two straight lines in the shape of a V. So we recognize that there is still a minimum point here, or a minimum value. And what else can we say? And also goes forever up on both the left and the right. Right, so that function isn't that interesting, but hopefully it's straightforward enough that we see the absolute value, kind of remember what it looks like. In this case, it's going to be a V. And that's really one of the key things that we want to get out of this part of the unit is the parent functions and really the general shape of it, so that we can see every time we see the absolute value of a function, absolute value function, we know what the shape's going to be look like. In this case, a V. Same thing with square root function. The general shape of it is going to be sort of this flat, I call it arrow, that only goes in one direction. And then with with a cubic, we have this sort of yin-yang shape to a cubic. So the last one we're going to look at is actually the most trickiest one. It's what we call the reciprocal function, or 1 over x. So why did we call it the reciprocal function? We'll see in a bit later on, but we know the notion of reciprocating. We've used it before, we've applied it before. So for example, when we divide by a fraction, we say we multiply by the reciprocal. And how do we understand the reciprocal? Well, basically we flip the fraction. In other words, the numerator becomes the denominator, the denominator becomes the numerator. And really that's what the reciprocal function does, is it sort of inverts or reciprocates our number that we have. So this one is tricky for a couple of reasons. One is that we can't start with x equals 0, because if it's 1 over 0, that's undefined. So we recognize that back in Unit 2, x being 0 is actually a restriction here. And most of the time when we looked at restrictions in Unit 2, we saw there was a hole in our graph. Well, in this case, we're going to see that's not a hole. So restriction is going to show itself in different ways. I didn't focus this much on this on Unit 2. I was focusing more on the holes. But here we're going to see that restrictions also show itself up in the graph in another way. So since we can't use 0, maybe the next one that starts for x that makes sense may be just 1. So here I'm going to use x is equal to 1. And so what's f of 1? Well, that's going to be 1 over 1, which is just 1. Okay, what happens when x is 2? Well, f of 2 is going to be 1 over 2. Remember, x is in the denominator. So that's the tricky part about this one. X is in the denominator. So when we sub in x for 2, 2 belongs up in the denominator. So really that's going to be a half. And when x is 3, well, f of 3 is just going to be 1 over 3, which is 1/3. Now, when we go the other way, we don't want to actually quite go into the negative. So what we want to go is a fraction that's between 0 and 1. So here we're just going to go back a half. So let's say what happens when x is a half. So here, when we say f of a half, this is really 1 over 2. In other words, we're dividing by a half, which is the same thing as multiplying by the reciprocal, which is 2 over 1, which is 2. So this is why it's called a reciprocal function. So whatever value we take for x, we actually just reciprocate it. In other words, flip it in terms of numerator and denominator. So here, f of a half is going to be 2. And then here, and notice I'm purposely choosing fractions where the numerator is 1. Because when I reciprocate it, then the 1 becomes the denominator, and then we get an integer. So here we get f of a third, which is just going to be 3. So let's plot this. So we don't have 0, but we have 1 comma 1, which looks like that. We'll have 2, that's a half, and then 3, that's going to be a third. And then we're going to have a half, it's going to be a 2, so 1 half comma 2. When x is a third, the y is 3. So how do we connect these dots? So I just want to explore a little bit about what the ends, what I call the ends, might look like. So what happens if I take a really big value of x? So let's say f of 1,000. What is that going to look like? Well, that's going to be 1 over 1,000. So in other words, when x is really big, f of x is actually really small, 1 over 1,000. So if I take f of 1,000,000, that's going to be 1 over 1,000,000, which is really, really small. And then we take, let's say x is 1 billion, so that's going to be 1 over 1 billion, which is even smaller. But the most important thing to recognize is as it gets smaller and smaller and smaller, as x gets bigger, we can never have the value 0. Even as 1 over 1 trillion, really, really close to 0, but in actuality it is not 0. I mean, the only way we get a 0 answer is when the numerator is 0. 0 divided by something is the only way we get 0. But we don't, we have 1, so we have a smidgen. So whenever we have a smidgen, we don't have 0. So what this graph looks like on this end is sort of, it keeps going and going and going. It's really, really close to 0, x as big, but we'll never touch it. So that's why this line kind of flattens out that way. And let's look at the sort of the reverse or the opposite. What happens if x is really small? So let's say 1 over 1,000. Well, f of 1 over 1,000 is going to be 1,000. So that's going to become really big. Likewise, when f is 1 over 1,000,000, so f of 1 over 1,000,000 is going to be 1,000,000. F of 1 over 1 billion is going to be 1 billion. So as x gets smaller, 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 the y value gets really, really huge. But one thing to note is that we can never have f of 0 because that's undefined. So our graph is going to look like on the other side of this. It's going to keep going up and up and up and up, really, really close to the y-axis. In other words, x equals 0, but we can never get there because x can never be 0. So this is how we can see, another way we can see that there's a restriction here, is that it gets closer and closer to that restriction, but it can never be it. So we're not actually done. We're actually halfway there. So that's another weird part of this function. This is actually 2 separate lines or 2 separate curves. So the other one that we want to explore is -1. So we'll look at the net when x is negative, and we think, well, is that even possible? Well, let's look at it. Well, f of -1 is going to be 1 over negative 1, which is negative 1. So it is possible. In this case, we get a negative answer. So likewise, we're going to go down by negative 1. So f of negative 2 is going to be 1 over, a little bit bigger, 1 over negative 2, which is just a negative a half. F of x is negative 3. So f of a negative 3 is going to be 1 over negative 3, which is negative a third. So likewise, going the other way is we want to work towards 0, but we want to take a portion of it or a fraction of it. So maybe we'll look at f of a negative a half. So that's going to be 1 over a negative 1/2, which is going to be a negative 2, or we're going to flip it. We just reciprocate the fraction. And likewise, we look at a negative a third. So f of a negative a third is going to be negative 3. So let's go off and plot that. So we got 1 and negative 1, 2 and a negative a half, 3 and negative a third, and then negative a half and 2, negative 2, and negative a third, and negative 3. So we're going to discover that likewise the same things are going to happen on this other side when x is negative as well. When x is very negative, so it has very large negative value. So negative 1,000, negative 1,000,000, negative 1,000,000,000. We're going to get a very small negative value. In other words, 1 over 1, negative 1 over 1,000, negative 1 over 1,000,000, negative 1 over 1,000,000,000. So here, again, it's going to get closer and closer to 0, but again, on this side, we can't get the answer 0. Okay, but we can get very close to it, but from a negative perspective. Likewise, if x becomes a very small negative value, negative third, or so negative 1,000, sorry, negative over 1 over 1,000, negative 1 over 1,000,000, negative 1 over 1,000,000,000. When we reciprocate that, we're going to get a very large negative value. So here the graph is going to go down here, but again, we get closer and closer to 0, but x in itself can't be 0. So what we see here is that that's where we see the restriction, and that in this case, let me try that again. X can get very close to 0, but it will never touch it. Okay, so this has a special name for it. So in this case, this line has the equation x equals 0, really a y-axis, x equals 0. So this is what we call an asymptote. So definition of an asymptote is the equation of a line. Let me do it right over here. Equation of a line where the function gets closer and closer to it, but never touches it. It really never reaches it in terms of a numerical answer. Okay, and we discovered that there's also another asymptote going this way, what we call horizontal asymptote, because we can never get the answer 0. We get very close to it, and from both the negative direction and the positive direction, we can get very close to it, but we can never ever get it. So again, this equation of this line is going to be y is equal to 0. So it gets closer and closer to the x-axis. In other words, y is equal to 0, but we'll never touch it. So I'm actually going to answer this other question first. Were there two asymptotes? Well, horizontal asymptote is going to be y is equal to 0, and our vertical asymptote is going to be x is equal to 0. So that actually helps us define our domain and range. So the domain here is going to be really x can be anything. No way we can look at it, but we cannot be 0. In other words, we cannot divide by 0. The range, in this case, well, we can get all possible answers, except that we can never get the answer 0. So hopefully, as I write that out, you can see that there's a direct correlation between the restrictions, or what the answer that we can get to, and our actual asymptotes. Okay, so special features that we can look at it. It's curved. It's discontinuous. In other words, the line is broken for this function, is not joined. It's not one continuous line. In this case, it's actually two continuous lines, so it's discontinuous, and it actually has two asymptotes. One vertical and one horizontal. And it's going to kind of be important to remember those asymptotes as we go off and sort of graph variations of the reciprocal function. So for homework, just want you to complete these 4 questions. So you're not going to do this in Desmos, but you're just going to do this through a table of values. Okay, so for me, the biggest hint is starting x equals 0 and see where you kind of lead to, and hopefully you can kind of see with this, 0 isn't going to be the best choice, and from doing the homework, hopefully you might have a better understanding what the better choice of starting x to be in order to graph these functions properly. I just do want to give you a hint on the very last one. We do the reciprocal. This one turns out to be a little bit tricky because now it's going to be 1 over x minus 1. So in this case, we can't start with x being 1 because 1 minus 1 is actually going to give us 0. So that sort of gives us a hint already that maybe because x can't be 1, that's actually a restriction. That's where the asymptote, in other words, x equals 1, our vertical asymptote is going to be. So we kind of draw that right here as a hint. That's where a vertical asymptote is going to be. In other words, our line's going to get closer and closer to that, but it can't touch it. So we actually want to maybe start with an x value of 2, and then work up from that. So 3 and 4. The idea here is that we want to go from here and start going up from there. But we want to work towards back our asymptote as a fraction now. So here maybe we look at 1 1/2 and then 1 1/3. Okay, so we're getting closer and closer to the 1, but not quite getting there. Likewise, we don't actually want to start with x equals -1 because actually we're going to be too far away. We actually want to start looking at x equals 0 because let's get this a little closer to our vertical asymptote, x equals 0, and again working the negatives, going to be -1, -2. But now we're actually going to work closer to the the vertical asymptote. So here we may want to go to 1/2, and then tricky part here is now we actually want to go to 2/3. So those are the other points that you might start working with in order to graph this properly.